Welcome to this Masterclass Explainer. I'm so thrilled you're tuning in because we're jumping right into an ascending journey through the periodic table. We're going to start with the foundational concepts, the bedrock of how elements are classified, and then we're going to climb. We'll level up step by step until we're cracking the exact algorithms to find element positions, and finally, we'll conquer those advanced JEE and NEET edge cases that separate the good students from the absolute masters. Get ready to rethink how you look at the elements.
Okay, here's our agenda for today. 1. The modern periodic law. 2. The position-finding algorithm. 3. ISC extras like IUPAC naming. 4. JEN and NEET configuration anomalies. And 5. The F-block and extended predictions.
Let's kick things off with Section 1, the modern periodic law. For a long time, chemistry relied heavily on Dmitry Mendeleev's periodic table, which was organized based on atomic weight, or mass. And honestly, it worked beautifully for a while. It even allowed him to predict undiscovered elements. But it definitely wasn't perfect. There were some strange anomalies. Then in the early 20th century, Henry Moseley came along and completely flipped the script. He discovered that atomic mass isn't actually what defines an element's fundamental nature. It's the atomic number, represented by the letter Z. That's the number of protons in the nucleus, and it turns out that is the true fundamental property of an element.
The direct result of Moseley's breakthrough is the long-form periodic table we use today. By organizing elements purely by increasing atomic number, their physical and chemical properties naturally become periodic functions. This elegant arrangement creates the 18 vertical columns we call groups and the 7 horizontal rows we call periods. It's an incredibly logical system once you realize the atomic number is the key to everything.
Now, before we get into the heavy math and crack the algorithm for this table, I need to remind you to hit that subscribe button for the Masterclass 11 and 12 YouTube channel. Also, make absolutely sure you join our Telegram channel. The link is right down in the description. That is exactly where you can download all of our free notes, formula sheets, and PDFs. You are definitely going to want those resources handy as we move forward.
All right, Section 2, the position-finding algorithm. This is where things get really fun. To make this mathematical cheat code work, you absolutely need to burn the noble gases into your memory. They are our reference anchors. We've got helium at atomic number 2 in period 1, neon at 10, argon at 18, krypton at 36, xenon at 54, radon at 86, and oganesson at 118. Because these noble gases have completely filled electron shells, they sit at the very end of each period. So whenever you're faced with a random atomic number, your very first thought has to be, okay, which noble gas comes just before this?
So here is how that builds into a simple 3-step algorithm. Step 1, find that preceding noble gas. Step 2, to find the period of your target element, you simply take the period of that preceding noble gas and add 1. You're just starting a brand new shell. And step 3, write the condensed electronic configuration using the Aufbau principle. The subshell that receives the absolute last entering electron completely dictates which block the element belongs to.
The entire table cleanly groups into 4 distinct blocks, the S, P, D, and F blocks. If that last electron drops into an s orbital, your element lives on the far left. If it drops into a p orbital, it's strictly on the right. The d block elements, our transition metals, make up that wide middle section. And the F block elements, the inner transition metals, sit down at the very bottom. So an electronic configuration isn't just a string of numbers, it's a literal treasure map to the periodic table.
The next crucial step is mathematically determining the group once we know the block. For the S block, the group number is simply the number of valence s electrons, so either 1 or 2. For the P block, it's 12 plus those valence p electrons. For the D block, you just add your n-1 d electrons to your ns electrons. But listen, pay close attention to the F block. The F block is always group 3. That is a massive shortcut, and it's a special case we're going to revisit in the advanced section.
Awesome. Let's keep moving. Section 3, IUPAC Extras, focusing on IUPAC naming and some crucial math.
Now, what's incredibly fascinating is the exact mathematical proof Moseley used. He didn't just guess that atomic number was better than atomic mass. He proved it. He bombarded different metals with high-speed electrons, causing them to emit characteristic X-rays. When he plotted the square root of the X-ray frequency, that's the V in our formula, against the atomic number Z, it produced a perfect straight line. Plotting it against atomic mass did not. So this equation, the square root of V equals A times Z minus B, is the ultimate empirical proof that atomic number is the fundamental property of the elements.
Now imagine the intense drama when scientists started discovering super heavy artificial elements above atomic number 100. Naming disputes were everywhere. American and Soviet scientists literally fought over the discovery of element 104, calling it rutherordium and kerchitovium, respectively. To stop the chaos, IUPAC created systematic rules. You just build the name using numerical roots and slap ium on the end. So for z equals 101, you combine 1 for un, 0 for nil, and 1 for un, giving you un-nil-unium, symbol UNU. For 104, it's un-nil-quadium, UNQ. It completely eliminates the guesswork.
All right, let's dial up the intensity. Section 4, JEE and NEET configuration anomalies. This is the boss level. Standard off-bow rules are great, but competitive exams love to test you on the exceptions where experimental data completely defies our expectations. Let's look at palladium, atomic number 46. You'd totally expect its configuration to end in 4d85s2, but experimentally, it pulls both s electrons into the d subshell to achieve a fully filled, highly stable d orbital, so it's actually 4d10-5s0. Palladium is literally the only d-block element with 0 electrons in its s orbital. That is a massive trivia point. Then we have gadolinium, Z equals 64. Instead of 4f8, 6s2, one electron drops into the 5d orbital to leave the 4f subshell exactly half-filled at 4f7, giving it extra stability. And of course, you absolutely cannot forget the classic 3D series exceptions. Chromium at Z equals 24 shifts an electron to become 3d5-4s1, achieving that highly stable half-filled d subshell. Copper at Z equals 29 pulls a similar move, shifting an electron to become 3d10-4s1 for a fully filled d subshell. When you're tackling these entrance exams, always look out for these half-filled and fully filled stability anomalies.
We've reached our final stage, Section 5. The F-block and extended predictions.
I call this the F-block trap because it catches so many students totally off guard. Because the lanthanides and actinides are placed in 2 separate rows at the very bottom, people assume they have their own special group numbers. They don't. Every single element from Z58 to 71 and Z90 to 103 belongs to group 3. They are inner transition elements, and they're placed at the bottom simply to keep the main periodic table from becoming ridiculously wide and breaking the structural alignment of the other groups. Now let's play prophet. Elements 119 and 120 haven't even been synthesized yet, but our algorithm tells us exactly where they'll live. Applying what we've learned, the preceding noble gas anchor is Oganesson at Z equals 118, which closes out period 7. So to find the period for 119, we just add 1. We're opening period 8. The configuration for Z equals 119 will be Oganesson core plus 8s1, making it an S-block element in group 1, an alkali metal. Element 120 will be 8s2, putting it right next door in group 2. The algorithm works perfectly, even for elements that don't exist yet.
So, what does this all mean for you? I want to leave you with a quick challenge to test your new MasterClass skills. If a laboratory announces the discovery of element 121 tomorrow, based on the Aufbau principle and the algorithms we've practiced today, which block and which group would it officially belong to? Grab a piece of paper, use your Oganesson anchor, and trace exactly where that 121st electron has to go. Keep practicing those configurations, and I'll catch you in the next explainer.